So after our discussion of sequences, we're now going to shift our focus and our attention to the notion of a series. And of the two concepts, we're going to get a lot more work out of the idea of a series than we are of the sequence. The definition of a series is pretty straightforward. It's the sum of the terms of a sequence. So if you have a sequence and you add together all the terms, that produces a series. We can talk about a finite sequence. However, essentially all of our attention is going to be on an infinite sequence. And so you can have a finite series. However, essentially all of our focus, all of our attention is going to be on infinite series. And so, suppose we have a sequence defined by the rule, something straightforward, 1 over n squared. So the terms of that sequence are, as n equals 1, n equals 2, n equals 3, n equals 4, and so on. Then the sum of the terms of the sequence, and we write it this way: the sum as n goes from 1 to infinity of an, which we may write as the sum as n goes from 1 to infinity of 1 over n squared. That is the sum of the terms of that sequence. And so we can write, I'm going to simplify this, 1 plus 1/4 plus 1/9 plus 1/16 plus, and so on. Now, it is not immediately obvious, but it is in fact the case that it is possible to add together an infinite number of positive numbers and yet have that sum equal a finite value. That is not immediately obvious, but we'll discuss that as we go a little further along. So we have the series is the sum of the terms of a sequence. So if we have a different sequence, if Bn is the sequence 1 over n, then we may talk about the sum. Now, very often, if it is clear from the context, we will not write the index, but we assume this means n equals 1 to infinity, unless there's a specific reason otherwise. There are going to be a few places where we will specify these to be something slightly different. However, if it is clear from the context, then we very often suppress writing the indices. How about if I do this one more time? N equals 1 to infinity of Bn. That's the sum. N goes from 1 to infinity of 1 over n. And the terms of this sequence are 1, comma, 1/2, comma, 1/3, 1/4, and so on. And so the sum is 1 plus 1/2 plus 1/3 plus 1/4 plus, and so on. I had an instructor who said all you do is you replace the commas with pluses. And so that's a way to think of it. That's the sum of that sequence. So the series is the sum of the terms of a sequence. And at its heart, that's all that's going on. It is not obvious, like I said earlier, but it is possible to have the sum of an infinite number of positive values. It is possible that sum might be infinite. Or it's possible that some might not be. As it turns out, we will see this later on, it turns out this particular series, this sum is infinite. In this particular series, this sum is finite. That is not obvious, but we will talk about that and discuss that later on. Now, it is possible for this series to, the word is, converge. So a series converges. A series converges as opposed to a sequence. So a sequence converges. Now, we've talked about that before. A sequence converges if the limit right? If the limit is a finite value. But the series converges if the sum is a finite value. And that's an important distinction. We use the same terminology, but they're applied to different ideas, and the requirement is different. A sequence converges if the limit is finite. A series converges if the sum is finite. So, given, and as we've seen, given any particular sequence, there exists, so here, given a particular sequence, we can form the series. This is called, or we will call this, the associated series. So every sequence has an associated series, and every series has an associated sequence. Here, this was 1 over n. So this sequence and this series, they are associated with each other. This sequence is associated with this series. All right? It is in principle possible for the sequence to converge, but the series might not. Or they might both converge, or potentially any mix is possible. We're going to see there actually are a few restrictions on that. But at this level, at this point in the game, we don't necessarily know that if the series converges, does that necessarily mean the sequence converges, or vice versa. All we have so far is the definition of sequence convergence is the limit is finite. The definition of series convergence is the sum is a finite value. And so those it's very similar, but those are different notions, different ideas. So let's take a bit of a review here. Let's go back to an example from our sequence study. And suppose that we have this sequence, just a little review here. Suppose we have the sequence 1/2, 3/4, 7/8, 15/16, 31/32, and so on. And so my question is, if this is, let's call this AN. So those are the terms of the sequence. All right, so this sequence gives those terms. Can we find the generic term, the expression that is the generating rule for that sequence? Well, look at the denominators. 2, 4, 8, 16, 32. We see what the denominators are. The denominators, do you recognize those? Those are the powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. So the denominators are 2 to the nth power. But look at the numerators. The numerators are that number minus 1, that number minus 1, that number minus 1, and so on. And so sure enough, this is 2 to the n minus 1. All right? Now, a question might be, does this sequence converge? There's no series anywhere here. All we have is a sequence. What does it mean, converge? Does this sequence converge? Well, what is required for a sequence to converge? A sequence converges, so a sequence converges if and only if the limit, as n goes to infinity, of the defining rule is finite. Is this a finite number? So let's find out. We take the limit, as n goes to infinity, of the defining rule. 2 to the n minus 1 over 2 to the n. This is infinity over infinity if you do direct substitution. It's not too hard to see, 2 to the n power is, 2 to the infinity power is infinity. it's not too hard to see that this is infinity over infinity. We could use L'Hopital's rule, but that would require us to recall the rules for derivatives of exponential functions with bases other than e. I'm going to go back to the procedure that we used back in Calc 1. You divide through by this dominant term in denominator. So I'm going to take every term in the numerator and denominator and divide by 2 to the n. So this limit is equal to this limit. This is not the only way to work this, but I'm going to work it this way. So everybody gets divided by 2 to the n. And when you simplify that, remember, you continue to write LIM until you actually do the evaluation. This is 1. This is 1 over 2 raised to the nth power. And this denominator is 1. Well, in the limit, it's clear that goes to 0. And so that limit is 1. And so what did we find out? What do we say? So does this sequence converge? Yes, it converges. Therefore, the sequence converges. Therefore, the sequence converges. And we say it converges to 1. If you were to plot these points, the points on the graph would approach a horizontal asymptote at 1. So the definition of sequence convergence is that the limit is finite. The way to think about that, or an alternate way to say the same thing, is that the graph approaches a horizontal asymptote, and it will approach the horizontal asymptote at that number. Remember, if this oscillates back and forth, then that limit doesn't exist. If this goes off to infinity or negative infinity, the limit doesn't exist. So there are a couple ways for this to fail, but if it succeeds, if that limit is a finite number, then we say the sequence converges, and in this particular case, the interpretation is the horizontal asymptote is at 1. So I want to keep this in my back pocket here just for a minute. If an is equal to 2 to the n minus 1 over 2 to the n, this converges. I'm going to use that a little bit later here, and so I'm going to just make a little note of that up in the corner here. So, let's follow the trail of the shift of attention, the shift of focus from sequence to series. All right? So, given a sequence, so it converges if the limit is finite. All right? From a sequence, we can form the associated series. Or vice versa. If you have a series given, you could backtrack to find the associated sequence, and that sequence would converge if the limit is finite. The associated series, we would say, is that converges. So what does it mean for a series to converge? The series converges if the sum is finite. All right? And then we have a new entity in play here. We have a new player in our game. It's called the sequence of partial sums. The sequence of partial sums. Given any series, you can produce the sequence of partial sums. Very often, this process is not reversible. These are interchangeable. You have one, you get the other, you have the other, you get the one. But this is very often not reversible. But given any series, you can form what is called the sequence of partial sums. And we're going to take a little bit of a look at that. What do we mean when we say sequence of partial sums, and what does it represent? What does it mean? What is it good for? So what I'm going to do is take a sequence. So example A. suppose our sequence is, let's make it something really, really, really basic. It's the constant sequence at 2. And 1 is 2, and 2 is 2, and 3 is 3, 2, and 4 is 2, and 5 is 2, and 50 is 2. So this is the terms of this sequence, right? The terms of the sequence are 2, 2, 2, 2, 2, and so on. All right? And so we have also, so this is the sequence. We also have the sum. So here's the sequence, here's the sum. And that would be the sum of these 2 plus 2 plus 2 plus 2 plus 2, and so on. Now, here's what we mean by so we've given a sequence, it may or may not converge. From that, we construct the associated series. It may or may not converge. This sum might or might not be finite. But then we have the sequence of partial sums. Now, what is that? So, I want to get a little space here. So for my series, I'm going to rewrite this. We have partial sum number 1. All that is the first term. All right? Partial sum number 2, try that again. Partial sum number 2 is you add together the first 2 terms, which in this case is 4. Partial sum number 3 is you add together 1, 2, 3, the first 3 terms, 6. And it's not too hard to catch this pattern. Partial sum number 4. That's 8, and so on. Well, it's not very hard to see. The first partial sum is 2 times 1. The second partial sum is 2 times 2. The third partial sum is 2 times 3. Fourth partial sum is 2 times 4. So what is the nth partial sum? Now what we have done is we have created, from these partial sums, we have created a new sequence. The new sequence that we've created is, let's write it over here, 2, 4, 6, 8, and that sequence will continue. This is the original sequence, the original sequence. Here's the original series, the associated series, and this is the sequence of what? This is the sequence of partial sums. That's where this phrase comes from. The sequence of partial sums. That is a new sequence all on its own. If we were just given this at the start, then the question is, this is term number 1, term number 2, term number 3, term number 4. What is term number n? Well, it should be pretty clear. 2 times n. The 10th term is 20. The 50th term is 100 because you're just adding 2's each time. And so we have S sub n. So given any series, S sub n, and if you like, you could really subscript. This gets to be a little bit cumbersome, but if you wanted to, you could put S sub a to indicate it's a, and then sub n, but that's very rarely done. It's clear from the context, the sequence of partial sums is 2n. So we have the original, there it is, 1, 2, 3. The sequence of partial sums is 2 times n. The original sequence, the associated series, the sequence of partial sums. All right? So let's try another here. Let's suppose our original sequence, this is an, so this is example A, here's example B with bn. This is 1 over 2 raised to the nth power. So what are the terms? The terms of that, when n is 1, this is 1/2. When n is 2, this is 1/4, 1/8, 1/16. This shouldn't have pluses in here. This is just a sequence. 1/32, 1/64, and so on. So there's the sequence. The partial sum is the series is easy. The series is just put pluses in between here. And so on. But now we want the sequence of partial sums. Now this is going to be a little bit more dicey than this little 2, 2, 2 all over the place. So let's go off to the side. I'm going to go up here a little bit and see if I have enough space. I'm going to see if I can construct the partial sums. Well, sum number 1 for this series. So S1 is just the first term, 1/2. So the first item in my sequence of partial sums is 1/2. All right? This is a sequence of partial sums, comma. Partial sum number 2 is you add together the first 2 terms. Well, 1/2 plus 1/4, I can do that. 1/2 and 1/4 is 3/4. That's the next term. All right? Comma. Partial sum number 3. 1/2 plus 1/4 plus 1/8. Let's see, common denominator is 8. That's going to be 4 plus 2 plus 1. That is 7/8. And let's do one more. S sub 4 is 1/2, 1/4, 1/8, 1/16. It is not obvious, but if you do the arithmetic, this adds up to 15/16. This is the sequence of partial sums. Now, this should be sort of familiar. We've already encountered this earlier in this discussion. In fact, this was that. 2 to the n, 2 to the n, 2 to the n, 2 to the n. This is 2 to the n minus 1, 2 to the n minus 1, 2 to the n minus 1. And so this is the sequence of partial sums is 2 to the n minus 1 over 2 to the nth. And that gives rise to that sequence. So there's nothing magic about this sequence or this sequence. This can be done in principle with any particular sequence. What becomes problematic is this, and this is where we're going to sort of take a little bit different route. What becomes problematic is this computation. This is about as simple as it gets, and we had to kind of figure it. This is not too bad, but we already had a lot of computation here. If this original sequence, and hence the associated series, if those are very challenging arithmetically at all, computing these values and actually finding that expression become extremely problematic. And so what we're going to do is find some other ways to go about doing this process so that we don't need to generate these partial sums. All right? So, what we're going to do then is investigate ways to find this or be able to determine and understand this behavior without needing to go all the way down to this partial sums. All right?